There is a place inside our own solar system where the sun is not the main source of heat. Go out about 10,400 times the Earth's distance from the sun, still well inside the boundary of everything our star holds, and the warmth left over from the Big Bang takes over, and it has kept 1 trillion frozen objects at 2.7 degrees above absolute zero ever since. Out there, our sun is a point of light about as bright as Sirius, and it throws no shadow. The objects are blacker than printer toner. One lap around the sun takes 31 million years. And in 76 years of looking, not one object in that entire region has ever been seen. By the end of tonight, you will know exactly what the journey to the Oort cloud would cost, and exactly what is waiting at the other end of it. Get comfortable. If you enjoy having the map of your own solar system quietly redrawn underneath you, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the phrase, our solar system, is going to mean something a little different than it did this morning. Now, let's gently drift into this. I want you to try something before we go anywhere, and it will only take a moment. Wherever you are right now, lying down or sitting up, in a dark room or a lit one, I want you to point at the place we are going tonight. You cannot do it. That is not a trick, and it is not a riddle. There is no direction you can lift your hand toward that would be correct, because the place we are traveling to tonight is in every direction at once. It is above the ceiling and below the floor and behind your shoulders and out past the window, in a shell that wraps the sun completely, and any line you draw outward from where you are lying will eventually pass through it. If you point at the wall, you are pointing at it. If you point at your feet, you are pointing at it. There is no wrong answer, which means there is also no right one, and that is the first strange thing about the Oort cloud. Here is the second. There is no photograph. Not a blurry one, not a distant one, not a single frame taken by any instrument human beings have ever built. Every picture you have seen of the Oort cloud, the pale spherical haze around a bright point, the diagram with the little cutaway wedge so you can see the planets tucked inside, is a drawing. Somebody made it up, carefully and honestly, based on numbers. Nobody has ever seen it. Nobody alive will ever see it. And yet it has been on the map of our solar system for 76 years, and almost every astronomer on Earth would tell you without hesitation that it is really there. So settle in, because that is the shape of tonight. We are going to make a journey outward, slowly, from the room you are lying in to the outermost region that our sun still holds on to, and along the way almost everything you assume about that region is going to come apart in your hands. Not violently, just quietly, one number at a time. Let me give you the scale first, because it is the thing people get wrong most often, and it is genuinely difficult to hold in your head. The solar system you learned in school is the one that goes out to Neptune. Mercury, Venus, Earth, Mars, then the gap, then the 4 giants, and then Neptune at the end, at about 30 times the distance from the Earth to the Sun. That is the picture on the classroom wall. That is the picture in every animation. And if you have been paying attention to space news for the past decade or two, you probably also know about the Kuiper belt beyond Neptune, where Pluto lives, and maybe you know about the heliopause, the place where the wind blowing off our sun finally loses to the wind blowing between the stars. That boundary sits at about 120 times the Earth's distance from the sun. Both Voyager spacecraft have crossed it. When they did, the headlines said they had left the solar system. They had not left the solar system. They had barely started. The Oort cloud's outer edge is usually placed at 100,000 times the distance from the Earth to the Sun. Not 120. 100,000. If you take the volume of space inside Neptune's orbit, everything, all the planets, all the asteroids, every spacecraft we have ever launched, the entire solar system as it appears in every diagram you have ever seen, and you compare it to the volume of the sphere the Oort cloud fills, the familiar solar system is about 1 part in 37 billion of it. Let me put that a different way, because a number like 37 billion just slides off the mind. Imagine the whole solar system, out to Neptune, is a single room in a house. An ordinary room, the one you are in. On that scale, the Oort cloud is not the house. It is not the street. It is a sphere of empty space with a radius of about 3,000 rooms in every direction, up, down, sideways, all of it, and the room is the only part of it that anyone has ever been in, or ever photographed, or ever will. There is another way to feel that number, and it uses light. Sunlight takes 8 minutes and 20 seconds to reach your face. It takes about 4 hours to reach Neptune. It takes about 16.5 hours to reach the place where the Voyagers crossed out of the solar wind. And it takes about 578 days, a year and 7 months of continuous travel at the speed of light, to reach the outer edge of the Oort cloud. Light, which crosses the entire span from the Sun to the Earth in the time it takes you to soft-boil an egg, needs longer than a pregnancy and a first birthday to get from our star to the place we are going tonight. And it is still, by every standard definition, inside our solar system. And here is the part that makes it worth 2 hours of your night. Almost everything the Sun holds on to is out there. Not almost everything by mass. By mass, the Sun itself is virtually all of it, and Jupiter is most of the rest. But by count, by number of individual objects, by sheer population, the overwhelming majority of the bodies gravitationally bound to our star are not planets, and not asteroids, and not anything you have heard of. They are frozen objects at least a kilometer across, sitting in the dark, and there are something like 1 trillion of them. There are more objects out there than there are stars in the entire Milky Way galaxy, by a factor of several hundred. 1 trillion objects. And not one of them has ever been seen. I want to be very precise about that, because it is the load-bearing fact of this entire video, and I do not want you to think I am being poetic. In 2014, the astronomer Hans Rieckmann published a review of the Oort cloud and long-period comets in the journal Meteoritics and Planetary Science, and he described the situation in terms that leave no room for misunderstanding. The Oort cloud, he wrote, remains an unobserved intellectual concept, inferred from the statistics of comet orbits. Not a photographed place. Not a measured place. A concept, a place we deduced, from evidence that fell out of it and landed on us. You will hear that sentence again tonight, in a different mood, when we understand what it costs. Because a place you cannot see is also a place you cannot travel to in any ordinary sense. You can travel to Mars. You can point a telescope at Mars, watch it move, calculate where it will be in 8 months, and aim. You can travel to Pluto, and we did, and it took 9.5 years, and the pictures came back, and there were mountains of water ice and glaciers of frozen nitrogen, and it was one of the great days in the history of exploration. But you cannot travel to the Oort cloud in that way, because there is nothing to aim at. There is no dot in any telescope. There is no ephemeris. There is no arrival. There is a region, defined statistically, with edges nobody can specify, containing objects nobody has located, and if you launched tomorrow at the fastest speed we have ever achieved, you would spend longer getting there than our species has spent doing agriculture. So what would happen? What would it actually be like? Not the artist's impression, not the diagram, but the real thing. What would you see out of the window on the way? What would the sun look like from out there? How cold would it be? And what exactly would be keeping it warm? And how would you know when you had arrived? And when you got there, what would actually be around you? By the end of tonight, you are going to know the answer to every one of those questions. Some of them are going to be much stranger than you expect. One of them, the last one, the one the whole video is built toward, is going to change what the phrase "our solar system" means to you, and I am not going to touch it until the very end. But we cannot start out there. We have to start with how anyone ever knew the place existed at all, because that story is the strangest part of the whole business, and it begins with a man in the Netherlands, in a cold January, holding a list of 19 comets. Leiden, in the Netherlands, is a town of canals and low brick houses about 30 miles from the North Sea, and in January of 1950 it would have been grey and wet and cold in the way that the Dutch coast is cold, which is not dramatic but is very persistent. The observatory there is one of the oldest in the world. Its director at the time was a man of 49 named Jan Hendrik Oort, and on the 3rd of January that year he published a paper that added a new region to the map of the solar system without looking at it even once. The paper appeared in a journal called The Bulletin of the Astronomical Institutes of the Netherlands, Volume 11, Issue 408, running from page 91 to page 110. Its title was The Structure of the Cloud of Comets Surrounding the Solar System and a Hypothesis Concerning Its Origin. I want you to notice the last 5 words of that title. A hypothesis concerning its origin. Oort put the caveat in the title. He knew exactly which part of what he was doing was solid and which part was a guess, and he labeled it before anyone else could. You should know who this man was before we look at what he did, because it changes how the argument feels. Oort was not a comet specialist making a lucky observation. He was, by 1950, one of the most consequential astronomers alive. 23 years earlier, as a young researcher, he had confirmed that the Milky Way rotates, that the whole disk of stars turns, and turns differentially, so the inner parts sweep round faster than the outer parts. He worked out the mathematics describing that rotation near our Sun. The constants in that description still carry his name. He established that we are not near the center of the galaxy, but far out in the suburbs of it. And he was one of the first serious voices arguing that most of the mass in a galaxy is invisible, that the stars we can see do not add up to enough gravity to explain the motions we measure. When Jan Oort told you that something was out there that you could not see, he had a track record. Now, the method. And the method is the strangest and most beautiful part of this entire story, so let me take it slowly. Comets come in 2 families. Some of them go round the sun on short leashes, a few years, a few decades, tidally, in more or less the plane of the planets. Halley's Comet comes back every 76 years or so. Those are the regulars. But there is another kind, comets that appear once, brighten, swing round the sun, and leave, on orbits so long that they will not be back for tens of thousands of years, or hundreds of thousands, or ever. They are called long-period comets, and in Oort's time, there were only a handful for which anyone had computed a reliable orbit by hand, which was the only way it could be done. Oort had 19 of them. Now here is the move. When you compute a comet's orbit, you do not just get where it is. You get the whole ellipse, the entire path, including the far end of it, the point where the comet is at its greatest distance from the sun before it turns around and starts falling back in. That far point is called the aphelion. Every comet carries in its trajectory a record of where it came from, the way a stone thrown through a window carries, in its arc, a record of the hand that threw it. Oort did not look at where his 19 comets were. He looked at where their orbits said they had been, and they were not scattered. That is the thing. If long-period comets came from nowhere in particular, from all across the outer solar system at every possible distance, their aphelia would smear out evenly across an enormous range, and there would be nothing to see. Instead, they piled up. A conspicuous number of them turned around at distances on the order of 20,000 times the Earth's distance from the Sun and beyond. There was a concentration. There was a bump in the data where no bump should be. Oort's own reading of it in the paper was that these comets were arriving from a reservoir sitting somewhere between 50,000 and 150,000 times the Earth's distance from the Sun. That was the first fingerprint. Here is the second, and it is the one that decides the shape of the thing. Everything in the solar system that belongs to the solar system's disk arrives and leaves in the disk. The planets orbit within a few degrees of a single flat plane. The asteroids do. The Kuiper Belt objects mostly do. The whole system is a phonograph record with a bright light at the middle, and things that live on the record stay on the record. But the long-period comets do not. They come in from everywhere. From above the plane, from below it, at right angles to it, going around the Sun the wrong way as often as the right way, with no preferred direction of any kind that anyone has ever been able to find. Whatever they were falling out of was not a disk. A disk cannot send you objects from directly overhead. Only a sphere can do that. So the flatness of the solar system, the flatness that defines every diagram, every orrery, every model hanging from a school ceiling, stops somewhere out there, and beyond it the Sun is wrapped in something that has no plane at all. That is the discovery. 19 comets, a clustering, and an absence of any preferred direction. From those three things came a region larger than everything else the Sun owns put together. That clustering has a name now. Astronomers call it the Oort spike, and it is still the single strongest piece of evidence for the cloud's existence. If you take every long-period comet ever recorded and plot them not by distance but by a quantity that measures how tightly bound they are to the Sun, the ones on their very first pass into the inner solar system, the genuinely new ones, the ones that have never been here before, do not spread out. They pile into a narrow spike at exactly the value that corresponds to a reservoir tens of thousands of times the Earth's distance from the Sun. Every survey since 1950 has added comets to that plot, and the spike has never gone away. It has only got sharper. Oort was not quite the first to have the idea, and it matters that we say so. 18 years earlier, in 1932, an Estonian astronomer named Ernst Öpik had argued on theoretical grounds, from the dynamics rather than from the comet catalogue, that a star like the Sun should be surrounded by a distant cloud of comets held loosely at enormous distances. He got there first, from a different direction, and for that reason you will sometimes see the region called the Öpik-Oort cloud, particularly in European papers. What Oort added was the evidence. Öpik said it should exist. Oort showed that the comets say it does. And here is what I want you to sit with, because it is the sentence this whole video keeps coming back to. The Oort cloud was discovered by counting the wreckage, not by looking at it, not by pointing anything at it, by taking the debris that fell out of it, arriving one comet at a time across centuries of patient European observation, and reasoning backwards from the shape of the fall to the shape of the thing that dropped it. It is the same logic you would use standing at the bottom of a cliff in the dark, surrounded by fallen stones, working out how high the cliff must be from how hard the stones hit. You never see the cliff. You never need to. It is forensic astronomy, and it worked, and it is still the only method there is. There is a comparison worth making here, because it shows you how unusual this situation is. The Kuiper belt, the flattened ring of icy bodies just beyond Neptune, where Pluto lives, was proposed on similar grounds in the 1940s and 50s by Kenneth Edgeworth and then by Gerard Kuiper. It was an inference too at first. And then in 1992, astronomers found the first object in it, a faint, slow-moving speck, and the inference became a place. The wait was about 40 years. Oort's cloud has now been waiting 76, with better telescopes every decade, and it is still waiting. Oort himself lived until 1992. He was 92 years old, and he died in November of the year the first Kuiper belt object was announced. He never saw a single object from the region he found. That last part is the part people find hardest to believe. 76 years have gone by. We have put telescopes in orbit. We have imaged the shadow of a black hole. We have detected the collision of neutron stars by the wobble it put into the shape of space itself. We have found more than 5,000 planets around other stars, some of them smaller than the Earth, some of them so far away their light takes thousands of years to arrive. And in all that time, in all of that extraordinary expansion of what can be seen, not one object has ever been confirmed sitting in place inside the Oort cloud. Not one. The best we have, and we will come back to them, because they are wonderful, are a small number of objects on enormous elongated orbits that dip close enough to be photographed at the very bottom of their fall, and then vanish back out into the dark for thousands of years. Everything else is inference. The trillion objects, inferred by extrapolating from how many comets we see falling in. The 5 Earth masses inferred from the trillion objects. The spherical shape inferred from the arrival directions. The temperature not measured at all, but calculated from physics. The composition measured, but measured on objects that had already left the region and were coming apart in the sunlight while we watched them. We are about to travel to a place we have described in enormous quantitative detail and have never once looked at. So let us find out what that actually costs. Because the first thing anybody wants to know about a journey is how long it takes, and the answer to that question is where the word terrifying in tonight's title starts to earn itself. There is a spacecraft leaving right now, and it left before most people listening to this were born. Voyager 1 went up on the 5th of September 1977 from Cape Canaveral, on a rocket that has not existed for decades, carrying a computer with about 69 kilobytes of memory, less than a single photograph on your phone, and a radio transmitter that puts out about 23 watts, which is less power than the bulb in a refrigerator. It is the fastest object our species has ever sent away from the Sun on a permanent trajectory, and it is currently moving outward at about 17 kilometers every second. That is roughly 61,000 kilometers an hour. It would cross the United States in about 4 minutes. That is our yardstick. Everything about the length of this journey is going to be measured against that little machine, still going, 49 years out. So, the inner edge of the Oort cloud. Depending on which paper you read, that is somewhere between 1,000 and 2,000 times the Earth's distance from the Sun. Take the closer figure. Be generous. Be optimistic. Take the shortest version of the trip that anybody credible proposes. At Voyager 1's speed, you reach 1,000 times the Earth's distance from the Sun in about 279 years. Sit with that for a second, because it is the easy number. 279 years ago, it was 1747. There was no United States. There were no photographs, No vaccines except the very earliest experiments with smallpox. No anesthetic, no electricity in any usable form, no germ theory of disease. Bach was alive and still writing. If you had launched this journey at the moment Bach sat down to compose the musical offering, you would be arriving at the innermost fringe of the Oort cloud round about now, this year, tonight, and you would not yet have properly begun. Take the other figure for the inner edge, 2,000 times the Earth's distance from the Sun, which is the value most papers actually use, and the trip becomes about 558 years. That launch would have had to leave in 1468, 24 years before Columbus, while Gutenberg's press was still a novelty. Now go further. The main body of the outer cloud starts around 20,000 times the Earth's distance from the Sun. At Voyager's speed, that is about 5,600 years. 5,600 years ago, the first cities in Mesopotamia were new. Writing had just been invented, and it was being used to keep track of grain. Nobody had built a pyramid yet. If a probe had left Uruk at the moment somebody first pressed a reed into wet clay to record a debt, it would be arriving at the inner boundary of the outer Oort cloud in our lifetime, and it would still have the entire cloud in front of it. Because the far edge is at 100,000 times the Earth's distance from the Sun. At 17 kilometers a second, that is about 27,900 years. 28,000 years ago there were mammoths. There were Neanderthals, just, barely, in the last few pockets of Europe. Nobody had domesticated an animal, planted a seed on purpose, or fired a pot. The oldest cave paintings in France and Spain were either being made at that moment or were already ancient. A probe launched then, by people who had no metal and no wheel, would be arriving at the outer boundary of the Oort cloud roughly now, and even that would only be the boundary in the one direction it happened to fly. It would have crossed the shell. It would not have crossed the cloud, because there is no crossing a sphere. You enter it and you leave it, and you have sampled a single thread through something enormous. And notice what has quietly happened to our vocabulary. When we talk about a trip to Mars, we talk in months. When we talk about a trip to Pluto, we talk in years, and New Horizons took 9.5 of them to get there, which felt like a long time and was reported as a long time. When we talk about the Oort cloud, months and years stop being useful units, and we start reaching for civilizations. That change of unit is not decoration. It is the single most important thing about this journey, and it happens early, somewhere out past a few hundred times the Earth's distance from the Sun. The natural way to measure the trip stops being a calendar and starts being a history book. Now, the obvious objection. Voyager is old. Voyager was launched with 1970s technology, and it was never designed to go fast. It was designed to visit planets. Surely we can do better. We can, a bit, and the honest arithmetic is not encouraging. The fastest object we have ever built is the Parker Solar Probe, which reached about 192 kilometers per second at its closest approach to the Sun, more than 11 times Voyager's speed. But that is a falling speed, not a cruising speed. It got that fast by dropping down the Sun's gravity well, and it is going to give all of it back on the way out. Nothing we have ever built cruises anywhere near that fast on a departing trajectory. But suppose we solved it. Suppose that tomorrow, by some enormous act of engineering, we could launch something at 10 times Voyager's speed and hold it. What does that buy us? It buys us this. 279 years becomes 28. 5,600 years becomes 560. And 27,900 years becomes 2,790. That is the whole return. A tenfold improvement in the fastest thing our civilization has ever made, an improvement we have no idea how to achieve, converts a journey longer than the history of agriculture into a journey longer than the history of Christianity. You do not escape this problem by going faster. You just change which century of human history you have to compare it to. The distance is not an engineering challenge with a solution at the end of it. The distance is a fact about the shape of the solar system, and it does not negotiate. And there is a quieter constraint underneath that one, which is that everything we have just calculated assumes you are only passing through. All of those numbers are flyby numbers. They are the time it takes to reach a distance while still moving at full speed, the way Voyager reached the outer planets and kept going. If you wanted to stop out there, to hold station, to stay, to actually loiter in the Oort cloud and look around, you would have to shed every bit of the speed you spent centuries building up, and the fuel to do that has to be carried the whole way, which makes the ship heavier, which makes the acceleration harder, which makes the trip longer. Arriving somewhere and stopping somewhere are entirely different problems, and the second one is much worse. For tonight, assume we never stop. Assume the whole journey is a fall-through, at speed, in the dark. There is one more way to feel it, and it is the cleanest, because it removes spacecraft from the picture entirely and uses the only speed that cannot be improved on. Light. Sunlight reaches your face in 8 minutes and 20 seconds. It reaches Neptune in about 4 hours. It reaches the place where the Voyagers crossed out of the solar wind in about 16.5 hours. So if you stood there and shone a torch back at the Earth, the beam would arrive not quite a day later. Now take it to the Oort cloud. Light reaches the inner edge in about 5.8 days. And it reaches the outer edge in about 578 days. That is a year and 7 months. At the speed of light. In one direction. Which means something very practical for anybody actually trying to run this mission. If you had a probe out there and you sent it an instruction, the instruction would arrive 19 months later, and the confirmation that it had been received would come back 19 months after that. Every single exchange, every question, every correction, every check that the thing is still alive, costs you more than 3 years, and there is no cleverness that shortens it. Not better antennas, not better computers, not better anything. The delay is the distance, and the distance is not going anywhere. So that is what the journey costs in time, somewhere between 3 centuries and 300 centuries, depending on how far in you are willing to call arrival, and no realistic technology changes the shape of that answer. But time is the easy problem. Time is just waiting, and waiting is survivable in principle. You build the thing well, you hand the operation down, you wait. The hard problem is the one nobody thinks about until they try to draw the mission on paper. And it is this. You have your ship, and you have your centuries, and you are ready to leave. Which way do you point it? Picture the wall of a mission control room, any mission control room, and the thing that is always on it. A display with a little icon of a spacecraft, a curved line showing where it has been, a dotted line showing where it is going, and a target at the end of the dotted line. That target is a dot. It has a name and coordinates and a predicted position for every second of the next decade, and the entire discipline of navigation exists to make the spacecraft and the dot arrive in the same place at the same moment. Now take the dot away. That is the situation with the Oort cloud, and it is the first genuinely strange thing about traveling there. When we flew to Pluto, we knew where Pluto was. We had watched it for 85 years. We could predict its position at the moment of encounter to within a few tens of kilometers, which is why New Horizons, after 9.5 years and 5 billion kilometers, arrived within about a minute and a half of its predicted time. Everything about that mission was possible because there was something to aim at. There is nothing to aim at out here. There is no object in any catalogue whose position we can predict, because there is no object in any catalogue at all. Every one of the trillion bodies out there is unlocated. We do not know where a single one of them is. We know, statistically, that they are there, the way you know a beach has sand grains on it without knowing where any particular grain is sitting. You might think this hardly matters. You do not need to aim at a specific comet, you just need to get out to the right distance, and you will be inside the region by definition. And that is true, and it is exactly why the problem is stranger than it first looks. There is a choice buried in it too, and it is not an obvious one. If the destination is a sphere, then in principle any heading will do, but not all headings are equal in practice. The inner part of the cloud is thought to be flattened toward the plane of the planets, more like a thick donut than a shell, which means a probe launched along the plane spends longer in the denser region, and a probe launched straight up leaves it sooner. Against that, launching along the plane means you spend the first part of the journey crossing the Kuiper belt and the scattered disk, where there is dust and debris. Launching upward gets you out of the traffic almost immediately. Neither consideration decides anything, because we do not know the shape of the inner cloud well enough for the difference to be calculable. So the first decision anyone would have to make about this mission, which way to go, is a decision that cannot currently be made on evidence. Because if there is nothing to aim at, then there is also nothing to steer by. And that turns out to matter enormously, in a way that has nothing to do with hitting a target and everything to do with knowing, at any point in the journey, where you are. Here is how deep space navigation actually works today. The Deep Space Network, 3 big dish complexes spaced around the Earth, in California, in Spain, and in Australia, sends a radio signal to the spacecraft. The spacecraft sends one back, and by timing the round trip you get the distance to within meters. By measuring the Doppler shift of the return signal, you get the speed along the line of sight to millimeters per second. By comparing the signal arriving at 2 dishes on opposite sides of the planet, you get the angle. It is a superb system, and it works out to the edge of the heliosphere and beyond. Voyager 1 is tracked this way right now, at more than 25 billion kilometers. But it depends completely on the Earth. Every one of those measurements is made from here. And the further you go, the weaker the returning signal gets, falling off as the square of the distance, so a probe at the outer Oort cloud would come back roughly 200,000 times fainter than Voyager does today, from more than 400 times as far away. At some point on a journey like this, the radio link is no longer a reliable service. It is an occasional gift. So the ship has to know where it is by itself. And the traditional way a ship does that is by looking out of the window. That is not a metaphor. Spacecraft navigate by stars. There are star trackers on essentially everything we launch, small cameras that photograph a patch of sky, match the pattern against an on-board catalogue, and work out precisely which way the vehicle is pointing. And that works beautifully for orientation, for knowing which way you are facing. It tells you nothing at all about where you are. To get position from stars, you need parallax. You need the stars to shift, relative to each other, as you move, the way a nearby lamppost slides against distant buildings when you walk past it. And here is the number that ends the discussion. The nearest star to the Sun is Proxima Centauri, at about 268,000 times the Earth's distance from the Sun. Travel all the way to the far edge of the Oort cloud, 100,000 times the Earth's distance from the Sun, the full 28,000-year journey, the whole thing, and you have moved about a third of the way to the nearest star. That is enough to shift the very nearest stars noticeably, if you have an extremely precise instrument. But for the overwhelming majority of the sky, for the thousands of stars that make up the constellations, for anything more than a few dozen light-years away, the shift is smaller than the accuracy of the measurement, which means the view does not change. Let me put you in it, because this is one of those things that has to be felt rather than explained. You are at the window of a ship 1,000 times the Earth's distance from the Sun, further out than any object our species has ever built. You have been traveling for a very long time, and it occurs to you, in the way these things do at 4 in the morning, that you have no direct evidence you are moving at all. So you decide to prove it to yourself. You pick a star, a good bright one, off to the left, in the part of the sky you have been looking at for years. You take a marker and you draw a small ring on the inside of the window, right around it, so that the star sits exactly in the middle of the ring. And then you go and do something else. You come back in a year. The star is in the middle of the ring. You come back in 10 years. The star is in the middle of the ring. You come back in a century, and by now the ring is somebody else's, drawn by a woman who has been dead for 80 years, and the star is exactly, precisely, immovably in the middle of it. You have traveled hundreds of billions of kilometers since it was drawn. Nothing has moved. Nothing is going to move. The instruments say you are traveling at 61,000 kilometers an hour, and the window says you are standing still, and both of them are correct. And there is a twist inside that stillness which makes it slightly worse rather than better. The sky is not truly frozen. Over long enough periods the stars do move, not because you have gone anywhere, but because they have. Every star in the galaxy is on its own orbit, and over tens of thousands of years the constellations slowly deform. The Big Dipper's handle bends. Orion's shoulders drift apart. On the 28,000-year timescale of a journey to the outer edge, the night sky visibly rearranges itself into something a person from Earth would not immediately recognize. So the window does eventually change, but it changes because of things happening light years away, on their own schedule, having nothing to do with you. The one moving picture available to the traveler is a record of everybody else's motion, not their own. That is the part nobody puts in the artist's impressions. Not the cold, not the dark, not the distance. The stillness. You could travel outward for the entire history of human civilization, and the sky would agree, the whole way, to pretend that nothing was happening. And that has a consequence which sounds almost silly until you think about it properly. If the view does not change, and the radio has become unreliable, and there is no target to check yourself against, then somewhere along this journey, position stops being something you measure and becomes something you calculate. You know where you are because of where you were and how fast you have been going and for how long. The ship's clock becomes the only instrument that is actually reporting the journey. Everything else is scenery, and the scenery is a still photograph. So we have a ship and centuries, and a direction that does not matter very much because every direction is correct, and a window that will not tell us anything. At least we will be able to see what we came for when we get near it. Except that we will not. And the reason we will not is the next thing, and it is worse than the stillness. Hold your hand up in front of you, palm toward the ceiling, and look at it. Whatever light is in the room right now, that is roughly the amount of light your hand has been receiving for your whole life. If you were outside on a clear day, the sun would be delivering about 1,361 watts to every square meter of ground. Call it the output of a good electric heater, poured onto a patch the size of a doormat, continuously, for free. That number has a name, Astronomers call it the solar constant, and it is the baseline for everything that follows. Light obeys a very simple and very unforgiving rule. Go twice as far away and you get a quarter as much. Go 10 times as far and you get 1/100th. It is the same rule that makes a street lamp useless from 3 streets away, and out here it does something that is genuinely hard to picture. At 1,000 times the Earth's distance from the Sun, the inner fringe of the Oort cloud, sunlight has fallen to about 1.5 thousandths of a watt per square meter. That is roughly a millionth of what falls on your hand outdoors. At 20,000 times the Earth's distance, the beginning of the outer cloud, it is about 3.5 millionths of a watt per square meter. And at the far edge, 100,000 times the Earth's distance, it is about 1/10 billionth of the sunlight falling on your window right now. 1/10 billionth. If you took all the sunlight landing on a football pitch at midday and reduced it by that factor, what would be left would be roughly the light of a single candle, spread across the whole pitch. That is the illumination available to work by, out where we are going. And that is only half the problem. The other half is what you are trying to illuminate. We have a picture in our heads of what comets look like, and the picture is wrong. It comes from photographs of comets near the Sun, blazing white, trailing an enormous bright tail across the sky, and from the word snowball, which is the word everybody has been taught. Comets are made largely of ice, so we imagine the nucleus is white, like fresh snow, and that if you shone a light on one it would gleam back at you. It would not. Comet nuclei are among the darkest objects in the solar system. We know this because we have been to some. In March of 1986, the European probe Giotto flew through the coma of Halley's Comet and came within about 600 kilometers of the nucleus and sent back the first close photographs of a cometary body anybody had ever seen. What was expected was a bright, icy lump. What came back was a dark potato, a black, cratered, irregular object reflecting only about 4% of the light falling on it. That is darker than coal. Darker than fresh asphalt. When Rosetta spent 2 years alongside Comet 67P, 3 decades later, it found essentially the same thing, a surface reflecting around 6%, about the darkness of printer toner. The reason is the thing that has been happening to those surfaces for 4.5 billion years, and we will come back to it properly later, but the short version is that constant bombardment by cosmic rays has slowly cooked the outer layers into complex dark carbon compounds. The ice is still there, meters down. The outside is tar. So put those two facts together. The available light is about 1/10 billionth of daylight. The objects you are looking for reflect 4% of what hits them. The objects themselves are, at minimum, a kilometer across, which sounds large until you realize you are looking for them across distances of hundreds of millions or billions of kilometers. This is not a difficult detection problem. It is not a problem that better cameras solve. It is an absence of signal. There is no photon budget. The number of reflected photons arriving from a dark kilometer-wide rock at those ranges, under that illumination, is so small that the concept of an image stops applying. The same arithmetic is why we cannot find these objects from here, from Earth, with our very best telescopes, and it is worth doing that version too, because it explains something about the whole history of the subject. When we look at a distant object in reflected sunlight, the light has to make the trip twice. It falls off on the way out from the sun to the object, and it falls off again on the way back from the object to us. So the brightness of a body in the outer solar system, seen from here, drops as the fourth power of its distance. Move something twice as far away, and it becomes 16 times fainter, not 4. That fourth power is a wall. It is why we have found thousands of objects in the Kuiper belt at 30 to 50 times the Earth's distance from the Sun, and a mere handful beyond 100. Sedna, which we will meet later tonight, was found at about 90 times the Earth's distance, and was at the time the most distant object in the solar system ever observed. And Sedna is about 1,000 kilometers across, roughly the width of France, and unusually red and reflective. Take an ordinary black comet nucleus a kilometer wide and put it at 20,000 times the Earth's distance, and you have made it fainter by a factor with dozens of zeros after it. No telescope that could be built on any budget, on any time scale, using any technology we can currently describe, would see it. Fine, you say. Bring your own light. This is the natural human response, and I love it, so let us take it seriously. You have a ship. Put a searchlight on it. Put a laser on it. Illuminate the dark yourself. Here is why that fails, and it fails on arithmetic rather than on engineering. When you send light out and wait for a reflection, the fall-off happens twice. Your beam spreads on the way out, so the amount landing on the target falls as the square of the distance. Then the reflected light spreads on the way back, so what reaches you falls as the square of the distance again. Combined, the returning signal falls as the fourth power of the range. Double the distance, and your echo is 16 times weaker. Multiply the distance by 10, and your echo is 10,000 times weaker. This is why radar is a wonderful tool at the Moon, a useful tool at Venus and Mars, a marginal tool in the asteroid belt, and simply not a tool at all past Saturn. The most powerful planetary radars we have ever built, the great dish at Arecibo before it collapsed, the transmitter at Goldstone, could bounce signals off asteroids at a few tens of millions of kilometers, and at the very limit, off the moons of Jupiter. The distances between objects in the Oort cloud are measured in hundreds of millions to billions of kilometers. You would need to increase the transmitted power by a factor in the millions to compensate, and you would need to do it while running on a power supply small enough to carry for 28,000 years. So passive detection does not work because there is no light. Active detection does not work because the echo dies. And the third option, waiting for one of these objects to pass in front of a background star and briefly blink it out, has been proposed seriously, and it is the one technique that could in principle catch an Oort body from a distance. A study in 2009 examined whether the Kepler Space Telescope's extraordinary photometric precision could pick up such events. The trouble is that the objects are tiny, the sky is enormous, and the events last a fraction of a second and occur at random. No confirmed detection of an Oort cloud object by stellar occultation has ever been reported. Which leaves us with something worth stating plainly, because it is the operational reality of this entire journey. You could fly a spacecraft through the Oort cloud for 10,000 years and pass within a few million kilometers of 100 objects on the way, and never know that a single one of them was there. Not fail to photograph them. Not get a poor image. Never know. There would be nothing on any instrument. No blip, no shadow, no flicker. The region would present itself to your sensors as perfectly empty for the entire crossing, and the only reason you would believe there was anything out there at all is that a man in Leiden in 1950 noticed that 19 comets turned around in the same neighborhood. That is the dark. It is not the poetic dark of a night sky, which is full of stars and beautiful. It is a working dark, a dark that defeats instruments. And it is worth pausing on what it would actually be like to sit inside, because the answer is quieter than you might expect. It is not black. Look out of that window and the stars are all still there, every one of them, unblinking and steady with no atmosphere to make them twinkle, more of them than anyone on Earth has ever seen from anywhere, laid across the whole sphere of the sky, including the parts under your feet. The band of the Milky Way runs through it like a spill of milk on a dark cloth. It is, by any reasonable standard, one of the most beautiful views available anywhere. It simply contains no information about where you are, and it does not illuminate anything. You could hold your hand up to that window and you would not see it. There is enough starlight out there to fill a sky, and not nearly enough to cast a shadow. But if you cannot see the objects, you can still see the sun. It is behind you, and it is the one thing in the whole sky that is unambiguously yours, and for the first part of the journey it is still brilliant. The question is, what happens to it while you are gone? There is a scale astronomers use for brightness, and it is one of the oldest measuring systems in continuous use anywhere in science. It goes back to the Greeks, who sorted the stars into 6 ranks by eye, first magnitude for the brightest, 6th for the faintest anyone could see. The system survived, got made precise, and acquired a slightly awkward feature along the way, which is that it runs backwards. Smaller numbers mean brighter. The brightest objects have negative numbers. Here is the scale you need for tonight, and I want you to have it in your head, because we are going to walk down it. The faintest star you can see from a dark garden is about magnitude 6. Vega, one of the bright summer stars, sits at almost exactly 0. Sirius, the brightest star in the whole night sky, is minus 1.46. Jupiter, at its best, is about minus 2.9. Venus, the evening star, the one that makes people phone the police, gets to about minus 4.9. The full moon is around minus 12.7. And the sun, from where you are sitting, is minus 26.7. That gap between the sun and everything else is the reason the sky looks the way it does. It is why there is such a thing as day. One more thing about the scale before we use it. Each step of 5 magnitudes is a factor of 100 in actual brightness. So the difference between the sun in your garden and Sirius in your garden is not a difference of 25 units of anything. It is a factor of about 13 billion. That is how much of a head start our star has, standing on the Earth. And that entire head start is something the journey spends. Now let us take the sun out to the Oort cloud and watch what happens to that number. At 1,000 times the Earth's distance from the sun, the inner fringe, the 279-year mark, the sun shines at about magnitude minus 11.7. That is very close to full moon brightness. But it is not a moon, it is a point. All of that light concentrated into something the eye cannot resolve at all, a fierce little pinprick that would be genuinely painful to look at directly and would throw a hard, sharp-edged shadow of your hand onto the wall behind you. It is still, unmistakably, the sun. It is still the ruler of that sky by an enormous margin. Nothing else out there comes within 10 magnitudes of it. Keep going. At 20,000 times the Earth's distance from the sun, where the outer cloud properly begins, the sun has fallen to magnitude minus 5.2. That is roughly the brightness of Venus at its very best, seen from Earth, and slightly brighter. Think about what Venus actually does for you on a clear evening. It is lovely. It is the first thing out. It is bright enough that people mistake it for an aircraft. And it is completely, utterly useless as a source of light. It does not let you read. It does not let you see the ground. It does not cast a shadow. From the beginning of the outer Oort cloud, our sun is a Venus, the most beautiful thing in that sky, and functionally decorative. And it is worth filling in the rungs between those two, because the fall is smooth, and there is no moment where anything announces itself. At 2,000 times the Earth's distance, the Sun is minus 10.2, still moon-like, still commanding. At 10,000 times, minus 6.7, brighter than Venus, dimmer than the Moon, at the edge of being able to do anything for you. At 50,000 times, minus 3.3, dimmer than Venus now, brighter than Jupiter, an object you would point out to a child. And then the outer edge. Keep going. At the outer edge, 100,000 times the Earth's distance from the Sun, the number is minus 1.7. And here is where I want you to stop and check that against the list I gave you at the start. Sirius, the brightest star in Earth's night sky, is minus 1.46. From the outer boundary of the Oort cloud, our Sun is about as bright as Sirius. Marginally brighter. A third of a magnitude, which is a difference you could not reliably judge by eye without something to compare it against. Our star has become a star. Not metaphorically, photometrically. If you were born out there and someone handed you a chart of the sky and asked you to pick out the object that owns everything around you, the thing that holds the trillion frozen objects in your neighborhood in their orbits, the thing that made every planet, the thing whose gravity you have been circling for 4.5 billion years, you would not be able to do it by eye. You would have to be told which one it was. It would be one bright point among several dozen bright points, and it would not be the brightest thing in every part of the sky, and there would be nothing about it, nothing at all, that would mark it as different in kind from Vega or Arcturus or Capella. There is a second measurement that goes with the brightness, and it is the one that finishes the job. As you move away, the Sun does not only dim, it shrinks. From your garden, the Sun is about half a degree across, which is why eclipses work, and why it has a visible edge. At the far side of the Oort cloud, it is about 2/100ths of an arcsecond across. To give that a shape you can hold, the human eye can just about separate two things, 1/60th of a degree apart, which is about the width of a small coin held at arm's length. The Sun, at the outer edge of its own cloud, is roughly 3 million times narrower than that. There is no disk. There is no edge. There is no shape. There is a mathematical point of light, and the eye has no way to distinguish it from any other point of light in the sky. For a sense of how far past our experience this is, the most famous photograph ever taken of the Earth from a distance, the pale blue dot, was made by Voyager 1 from about 6 billion kilometers out, which is around 40 times the Earth's distance from the Sun. In that image, the Sun was still overwhelming, so overwhelming that its scattered light produced the beams of glare the Earth happens to sit inside. The outer Oort cloud is about 2,500 times further out than that camera was. Let me put you back at that window, because this is the moment worth being there for. You are traveling outward, and you have turned the ship so that the Sun is behind you, and you can watch it go. In the first years, it is exactly as it was. Fierce. Undeniable. You hold your hand up in front of the glass, and there is a shadow of it on the wall, small and crisp. Then the shadow softens. Not suddenly. Over decades, over your whole working life, so gradually that you only notice when you find an old photograph and see the edge it used to have. Then one year you hold your hand up and there is no shadow at all, only a faint darkening, and you understand that you have crossed something, though nothing happened and no instrument recorded it. Then the light stops arriving as light and starts arriving as a fact. It is a point, and it is bright, and it does nothing. And you find that you have started doing something you never did in the 1st century. You check. Before you look, you check the chart, to make sure you are looking at the right one. And the day you do that for the first time, without thinking about it, is the day the sun stopped being the sun and became a star you happen to know the name of. And there is a strange kindness in it too, which I do not want to skip past. That sky is not empty. It is the most complete night anyone has ever stood in. No atmosphere, no scattering, no glow from a city over the hill, no moon washing anything out. Every star holds perfectly still and does not twinkle because there is no air to make it. The Milky Way is a solid presence, not a suggestion. If you did not know which point was home, you would look out at that view and think it was one of the most beautiful things you had ever seen, and you would be right. The horror is not that it is bleak. The horror is that it is lovely, and that home is somewhere in it, indistinguishable. Now, that is what the sun looks like out there. But looking is not the only thing a star does for you. The other thing it does, the thing you never notice, the thing that has been true every second of your life, is keep you warm. So let us ask a very simple question. Out there, at 2.7 Kelvin, with the sun reduced to a bright point that casts no shadow, what exactly is keeping those objects at the temperature they are? The answer is not the sun. And it has not been the sun for a very long time. Let us step back for a moment and put together what we have, because we are about halfway out and the pieces have started to make a shape. We have a destination that cannot be pointed at, because it is in every direction. We have a discovery made without a single observation, from 19 comets and the places their orbits said they turned around. We have a journey of somewhere between 328,000 years, which does not meaningfully improve if you go 10 times faster. We have a window that will not tell you that you are moving, because the stars are too far away to shift. We have a darkness that defeats every instrument we know how to build, both the ones that look and the ones that shine. And we have a sun that fades over the course of the trip, from the ruler of the sky into an ordinary star you would need a chart to identify. That is 5 things, and every one of them is an absence. Nothing to aim at, nothing to see by, nothing to see, nothing to navigate by, nothing to keep you company. The journey to the Oort cloud is defined almost entirely by what is missing from it. Which makes the next fact the strangest one in the whole video, because it is a presence. There is something out there. It is not the sun, and it is not the objects, and it has been there longer than either of them. Start with the ordinary physics. An object sitting in sunlight warms up until it is radiating away exactly as much heat as it absorbs, and then it stops. That balance point is its equilibrium temperature, and it depends only on how much sunlight is falling on it, which means it depends only on distance. The rule turns out to be a very clean one. The temperature falls as the square root of the distance. Go 4 times further out, and the temperature halves. Run it. At the Earth's distance, that calculation gives about 279 Kelvin, which is 6 degrees below the freezing point of water, and close enough to the real answer to be respectable. At Neptune, 30 times further out, it gives about 51 Kelvin, cold enough that nitrogen is a solid. At 1,000 times the Earth's distance, at the inner fringe of the Oort cloud, it gives about 8.8 Kelvin. That is colder than liquid helium, which boils at 4.2, and it is the sort of temperature that in a laboratory requires a specialized refrigerator, a great deal of money, and a room full of equipment to maintain. Keep going. At 20,000 times the Earth's distance, the formula gives 1.97 Kelvin. And at the far edge, 100,000 times out, it gives 0.88 Kelvin. And both of those last 2 numbers are wrong. They are not wrong, because the arithmetic is bad. The arithmetic is fine. They are wrong because the universe does not go below a certain temperature, anywhere, and those numbers are underneath it. Here is the thing that is out there. About 380,000 years after the beginning, the universe had cooled enough that the fog of loose particles filling it finally settled into atoms, and the light that had been trapped and rattling around inside that fog was suddenly free to travel. It has been traveling ever since. It is still traveling now. It fills every cubic meter of space in the observable universe, in every direction, with no gaps, and because the universe has expanded by a factor of about 1,000 since it was released, that light has been stretched out of the visible range and down into microwaves. It is called the cosmic microwave background. It is the oldest thing anybody can see. And it has a temperature. That temperature is 2.725 Kelvin. Every object in the universe, everywhere, is sitting in that bath. Your body is in it right now, a tiny trickle of 13.8 billion-year-old light passing through the room, through the walls, through you, all the time. On Earth it is irrelevant, because the sun is delivering a heater's worth of energy to every square meter, and the background is delivering an amount so small it takes specialized instruments to detect at all. But the sun's contribution falls off with distance, and the background's does not. It is the same everywhere. It is the floor. And it is astonishingly uniform. When the COBE satellite measured the spectrum of that background in the early 1990s, the curve it produced matched the theoretical prediction for a perfect radiating body so exactly that when the result was shown at a conference, the audience stood up and applauded. The error bars were smaller than the thickness of the line on the graph. The temperature of the universe is one of the best measured quantities in all of science. Which is a strange thing to be able to say about the number that decides how cold the edge of our solar system is. So there is a distance at which the two cross over. There is a place where the heat you get from our star and the heat you get from the beginning of the universe are exactly equal. Set the two equal and solve, and that distance comes out at about 10,450 times the Earth's distance from the Sun. Inside that line, the Sun is the main thing keeping an object warm. Outside it, the Big Bang is. I want to make sure that lands, because it is very easy to hear as a piece of trivia, and it is not trivia. It means there is a surface, a sphere, roughly 10,450 times the Earth's distance out, sitting well inside the solar system's own gravitational boundary, comfortably inside the Oort cloud, where the Sun hands over. On the near side, our star is the reason the ice is at the temperature it is. On the far side, the reason is a bath of radiation released before the Earth existed, before the Sun existed, before there were any stars at all. The objects out there are being kept warm, and warm is the correct word. They would be colder without it, by the afterglow of the event that made everything. And nothing marks it. There is no boundary you cross, no reading that jumps, no instrument that clicks over. It is a line drawn by two curves intersecting in a region nobody has ever been to, and if you flew through it, you would have no way of knowing. The solar system has a thermal edge, and it is nowhere near where anybody puts the edge on a map, and it has no name. Run the numbers properly, adding both heat sources together, and the picture at the destination becomes very simple. At 10,000 times the Earth's distance, the true equilibrium temperature is about 3.3 Kelvin. At 20,000 times, about 2.9. At 100,000 times, about 2.73. That last number is worth staring at. 2.73. The cosmic microwave background is 2.725. The difference is 5/1000ths of a degree. Which means this. Take an object in the outer Oort cloud, one of the 4.5 billion years old, bound to our Sun, orbiting our Sun, unambiguously part of our solar system by every gravitational definition anybody uses, and measure its temperature. Then take an object in the middle of interstellar space, 30 light-years from here, belonging to nothing and nobody, and measure that. You will get the same answer to within a rounding error. Thermally, the outer Oort cloud is not part of the solar system. It is indistinguishable from anywhere else in the galaxy. Our star has stopped mattering. It is worth spending a moment on what that temperature actually means for the material, because 2.7 Kelvin is not simply very cold, it is a different regime. Water is frozen, obviously. Water is frozen out past the asteroid belt. But at 2.7, carbon dioxide is a solid, and carbon monoxide is a solid, and molecular oxygen is a solid, and nitrogen is a solid, and even those have almost no vapor pressure left. They are not slowly evaporating, they are simply locked. Nothing moves. Nothing sublimates. Nothing changes. In a laboratory on Earth, reaching 2.7 Kelvin requires liquid helium and then a further stage of cooling beyond it, inside a shielded apparatus, at considerable expense, in a volume you could hold in your arms. Out there, the universe maintains it for nothing, across a sphere containing something like 10 to the 49 cubic meters, and has done for billions of years without interruption. There is one more turn in this, and it is the sort of thing that only becomes visible once you know where the heat is coming from. If the temperature out there is set by the cosmic microwave background, and the cosmic microwave background cools as the universe expands, then the outer Oort cloud has been getting colder, not because anything has happened to it, but because the universe has grown. When those objects were assembled, 4.5 billion years ago, the universe was smaller, and the background was correspondingly warmer, somewhere around 3.9 or 4 Kelvin, rather than 2.7. So the outer Oort cloud has cooled by roughly 1.25 degrees since it formed, and none of that had anything to do with the Sun. Its thermal history is not a record of our star. It is a record of the expansion of the universe. And it is still falling. Those objects will go on getting colder, by fractions of a degree over billions of years, for as long as space keeps stretching. That is the first crack, and it is a real one, and it is going to widen. Because if the Sun is not the thing keeping those objects warm, it is fair to start asking what else out there the Sun is not doing. We will get to that. But first there is something gentler to look at, and it is one of the quietest facts in astronomy, how slowly everything out there is actually moving. Think of a bucket of water on the end of a rope, swung in a circle. If the rope is short, you have to swing hard. The bucket whips round, and if you slow down at all, it falls in on you. If you let out more rope, the bucket goes round more slowly and more easily, and you have to work less. Longer rope, gentler swing. It is one of the few pieces of orbital mechanics that everybody already knows in their hands, from childhood, without ever having been taught it. The Sun's rope out to the Oort cloud is 100,000 times the length of ours. The Earth is moving around the Sun at 29.78 kilometers every second. That is 107,000 kilometers an hour. You are doing it right now, lying in bed. In the time it takes you to read this sentence, you have moved about 150 kilometers sideways, and you will never feel a thing. At 1,000 times the Earth's distance from the Sun, the required orbital speed has fallen to about 940 meters per second. That is still fast, around 3,400 kilometers an hour, roughly 3 times the speed of sound at sea level. At 20,000 times the Earth's distance, where the outer cloud begins, it is about 211 meters per second. 758 kilometers an hour. That is the cruising speed of a passenger jet. If you are on a long-haul flight tonight, you are traveling faster than the objects at the start of the outer Oort cloud are traveling around the sun. And at the far edge, 100,000 times the Earth's distance, the orbital speed is about 94 meters per second. 339 kilometers an hour. That is slower than a Formula One car at the end of a long straight. It is slower than a Japanese bullet train at full speed. It is slower than the wind in the strongest tornadoes ever measured. Those objects, the frozen bodies that mark the outermost boundary of everything the sun holds, are drifting around our star at a speed that a good motorcycle could exceed. Escape velocity out there is not much better. At the far edge, the speed you would need to break free of the sun forever is about 133 meters per second. On Earth, escape velocity is 11.2 kilometers a second, which is why leaving requires a rocket the height of a building. At 100,000 times the Earth's distance from the sun, it is a bit under 500 kilometers an hour. The sun's hold on the outer Oort cloud is not a grip. It is barely a suggestion. And that is going to matter enormously in a little while, when we look at what else out there is pulling. But the numbers that really break the mind are not the speeds. They are the periods, how long it takes to go round once. At 1,000 times the Earth's distance from the sun, one orbit takes about 31,600 years. At 20,000 times, one orbit takes about 2,830,000 years. And at the outer edge, 100,000 times the Earth's distance, one lap around the sun takes about 31.6 million years. Let me convert that into things you know. Modern humans have existed for roughly 300,000 years. In that entire span, everything, all of it, from the first anatomically modern people in Africa, through every language ever spoken, and every city ever built, and every war ever fought, an object at the outer edge of the Oort cloud has completed about 1% of a single orbit. It has moved through about 3.5 degrees of arc. If you were watching it from above with a protractor, you would say it had not moved. Go further back. The dinosaurs were wiped out 66 million years ago. Since that afternoon, since the impact, since the extinction, since the entire subsequent history of mammals, primates, and everything else, an object out there has been round the sun roughly twice. Go all the way back. The solar system is 4.5 billion years old. In its entire existence, an object at the outer edge of the Oort cloud has completed about 140 orbits. 140. The Earth has gone round 4.5 billion times. Now I have been describing circles, and I should be honest that almost nothing out there is on a circle. The objects in the Oort cloud are on all sorts of orbits, many of them long and stretched, and a stretched orbit means the object dawdles at the far end and hurries at the near end. So an object whose orbit takes it out to the edge and back in toward the planets spends the overwhelming majority of its time out there in the slow part, creeping, and then makes one brief, violent dash through the inner solar system before climbing back out again. That dash is the only part we ever see. When a long-period comet crosses the Earth's orbit, it is moving at something like 40 to 50 kilometers a second, faster than the Earth itself. It comes in, it warms, it throws off gas and dust for a few months, it swings around, and it leaves. And for those few months, it is one of the most dramatic objects in the sky. Then it goes back to being the slowest thing in the solar system for the next several million years. There is a lovely consequence of that. A comet's visit is not merely brief in our terms, it is brief in the comet's terms too. An object with a 3-million-year orbit that spends, say, a couple of years in the region where the sun can do anything to it, is spending roughly 1 part in a million of its life being a comet. The rest of the time, which is essentially all of the time, it is a dark, frozen rock drifting in the cold, and the bright thing with the tail that we photograph and name and put on postage stamps is a momentary condition it passes through, once, and may never pass through again. And it usually is only once. A single trip through the planetary region permanently rewrites the orbit, because Jupiter and Saturn are enormous and they tug. Comet Hale-Bopp, one of the brightest comets of the 20th century, arrived in 1997 on an orbit with a period of roughly 4,200 years and left on one of roughly 2,500. In a few months of passing, the planets took 17 centuries off its schedule without anybody doing anything. Every long-period comet we observe is being altered by the act of being observable. There is something genuinely restful in that, and I do not want to rush past it, because it is one of the few things about this region that is not unsettling. We are used to space being violent. Stars exploding, black holes tearing things apart, collisions and jets and enormous energies. This is the opposite. The Oort cloud is the quietest place attached to our sun. Nothing out there is in a hurry. Nothing has weather. Nothing has seasons. There is no meaningful day and no meaningful year, because the year is 31 million of ours, and the light is the same in every direction anyway. An object out there could be turning slowly on its axis, in the dark, at 2.7 Kelvin, and the only thing that would happen to it in 10,000 years is that it would rotate. That is the entire event log. If you have ever wanted somewhere in the universe where nothing happens, this is it. It is a shelf, 3,000 rooms wide in every direction, containing 1 trillion objects that have been sitting completely undisturbed for the entire history of the Earth. And there is one more consequence of all that slowness which is worth having, because it changes what the region would look like from inside. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. The objects around it are drifting at a couple of 100 meters a second in every direction on unrelated orbits. Which means the ship is not overtaking a stately procession. It is the fastest thing for light years in any direction, moving through a population that is, relative to it, essentially stationary. If you could somehow see them, they would not sweep past. They would hang there, and very slowly slide, the way distant hills slide when you are on a train. Everything else in the solar system that we have ever flown past came at us. Out here, nothing comes at you. You go past it, and it never notices. Well, almost undisturbed. Not quite. Something does happen out there, on a rhythm of its own, and when we get to it, you will see that it is the thing that produced every comet you have ever seen. But before that, there is a much more immediate problem to deal with, and it is the one that our imaginary ship is about to run into. We have been traveling for 5,500 years. According to the best estimate anybody made before we left, we are about to arrive. How exactly are we going to tell? Every journey any human being has ever made has had a moment of arrival. There is a point where the ship's rail comes alongside the dock. There is a point where the wheels touch the runway. There is a point where the road sign says the name of the town. Even the journeys where the boundary is invisible have a moment attached to them. The pilot announces that you have crossed the equator. The phone buzzes to say welcome to a new country. Somebody hands you a stamp. Arrival is such a basic part of what a journey is that it does not occur to us to ask whether a journey could be built without one. This one is. Start with what the boundary actually is, because it is not what people assume. The inner edge of the Oort cloud is usually given as 2,000 times the Earth's distance from the Sun, but NASA's own material notes that it could be as close as 1,000. The outer edge is usually given as 100,000 times, but NASA also states, in plain language on its public pages, that the outer boundary is not sharply defined. Some estimates put it at 150,000. Some at 200,000. Some pull it in tighter. That is a spread of a factor of 2 on both ends, and it is not because anybody is being careless. It is because there is nothing there to be careless about. There is no surface. There is no shell of material with an inside and an outside. There is no membrane, no shock front, no density jump, nothing that a sensor could register. The cloud is a population that gets sparser as you go out, until eventually there is nothing left to be sparse, and the place where you decide to draw the line is a matter of convention. There is one definition that is not a convention, and it is worth having because it is the only honest answer to where the solar system ends. Around every star, there is a volume in which that star's gravity beats everything else. In our case, in which the sun's pull beats the collective tidal pull of the entire Milky Way. It is called the Hill sphere, and for the sun, it is usually put at somewhere between 1 and 2 light-years, which means the outer Oort cloud, at about 1.5 light-years, and the outer limit of the sun's gravitational authority are roughly the same surface. That is not a coincidence, and it tells you what the cloud actually is. It does not end because the material runs out. It ends because the sun runs out of grip. The edge of the solar system is not a place where there is nothing left. It is a place where our star stops being able to keep what is there. And there is a second transition hiding in the same region, and it is arguably more interesting than the outer one. Somewhere out there, the solar system stops being flat. Everything you have ever seen in a diagram, the planets, the asteroid belt, the Kuiper belt, lives within a few degrees of one plane. The outer Oort cloud does not. It is a shell, wrapped in all directions, which was Oort's second great deduction from the comet's arrival angles. So somewhere between the flat part and the spherical part there is a handover, a region where the disk dissolves into a sphere. Nobody knows where. Nobody knows how gradual it is. It is somewhere between a few hundred and a few thousand times the Earth's distance from the Sun, and no spacecraft has been within a factor of 5 of it. The heliopause, at least, is a real boundary. When Voyager 1 crossed it on the 25th of August, 2012, the instruments knew. The density of charged particles around the spacecraft jumped by a factor of 40. The cosmic ray count went up. It was a genuine physical transition, and there is a date attached to it, and there always will be. There is no equivalent for this. There is no day the Oort cloud starts. There is no instrument that could be built which would register the entry, because entry is not a physical event out there. It is a bookkeeping decision made on Earth by people using a model about a region they inferred. And then there is the second problem, which is the one that turns an anticlimax into something colder. Even once you are unambiguously inside, even 1,000 times deeper in than any conceivable boundary, you cannot confirm it because there is nothing near enough to find. Let us do the arithmetic, gently, because it is worth having exactly. Take the outer cloud, out to 100,000 times the Earth's distance from the Sun, and take the standard estimate of 1 trillion objects bigger than 1 kilometer across. Spread them evenly through that sphere. The average distance from any one object to its nearest neighbor comes out at about 16 times the Earth's distance from the Sun. 16. Uranus orbits at about 19. So if you are standing on an object in the outer Oort cloud, the nearest other object of any size is roughly as far away from you as Uranus is from the Sun. Not the nearest star, the nearest neighbor in the same cloud. the nearest member of your own trillion-strong population. The inner cloud is denser, and the answer is friendlier, but only in relative terms. Do the same calculation for the region between 2,000 and 20,000 times the Earth's distance, and the average neighbor spacing comes out at around 3 times the Earth's distance from the Sun. Call it 480 million kilometers, which is a bit more than the gap between Mars and Jupiter. You will sometimes see the separations described as tens of millions of kilometers, and that figure is real too. It describes the densest interior parts of the cloud under generous assumptions about how many objects there are. And the honest thing to say is that the spread between those answers is itself the finding. Nobody can tell you how far apart the things out there are, because nobody has ever located one of them. The best anybody can offer is a range that depends on which model you believe. But take the friendliest number in that whole range. Take the crowded inner cloud, tens of millions of kilometers between neighbors. 10 million kilometers is 26 times the distance from the Earth to the Moon. It is a distance at which a kilometer-wide black object, in the dark, with no light source, is not merely invisible. It is not detectable by any means we have discussed or any means anybody has proposed. So here is what arrival actually looks like. You have been traveling for 5,500 years. Today, according to the best estimate that existed when the mission launched, you cross into the Oort cloud. Nothing happens. The particle counters read exactly what they read yesterday. The magnetometer is flat. The star field is identical, the same stars in the same places, the same as they were a century ago, the same as they will be a century from now. The temperature outside the hull sits where it has sat for a very long time, a few degrees above absolute zero, set by the background radiation of the universe rather than by anything nearby. There is no dust. There is no gas. There is no signature. The nearest object of any kind is somewhere between 400 million and 2.5 billion kilometers away, and there is no way of knowing which direction it lies in, or whether the estimate is right at all, or whether the nearest one is actually 10 times further than that. Somebody enters it in the log. Crossed the outer boundary of the Oort cloud, they write, and they add the date, and the date is a guess, and everyone aboard knows it is a guess. And then they close the log and go to bed, and the ship keeps going, and the sky keeps not changing, and tomorrow is exactly the same. That is what it would be. Not a wall of ice. Not a swarm. Not the artist's impression with 100 glittering comets hanging in the frame. A number in a logbook, in an unchanged room, surrounded by nothing measurable for the next 22,000 years. And this is the moment I want to bring back the thing we started with. Remember, at the very beginning, that you could not point at it. You could not lift your hand in any direction and be wrong, and you could not lift it in any direction and be right. Well, now you are inside it, and you still cannot point at it. Not because it is in every direction, although it is, but because there is not one single thing in that entire region whose location you could indicate. You have traveled 55 centuries to stand in the middle of a place, and the place has not become more locatable. It has become less, because now you are inside it, and it is still not there. Which raises a question that has been waiting since about the 3rd minute of this video, and it is time to ask it properly. If you cannot detect anything in a region containing 1 trillion objects, how much stuff is actually out there per cubic meter? The answer to that is the strangest number in this video, and it is not the one anybody expects. Here is a jar of sand on a kitchen table, and here is a lecture hall. Tip the jar into the hall and spread every grain out evenly, floor to ceiling, wall to wall, so that each grain is hanging perfectly still in the air with a good gap around it. Now walk in. There is sand in that room. There is exactly as much sand in that room as there was in the jar. You did not lose any. But if somebody asked you what the room was made of, you would not say sand. You would say air, and you would be right, because the air in that hall weighs several hundred kilograms, and the sand weighs a few hundred grams. That is the situation in the Oort cloud, and it is worse than the lecture hall by a factor I want to build up to slowly, because it is the single most counterintuitive number in this entire subject. Let us take the two figures we need, and let us be careful about where they come from, because I am about to put them together, and I want you to be able to check the join. The first figure is the mass of the outer Oort cloud. The standard estimate is around 5 times the mass of the Earth. That comes from the population estimate, the trillion objects bigger than a kilometer, the billion objects bigger than 20 kilometers, combined with reasonable guesses about their sizes and densities. It is not a measurement. It is an extrapolation, and we will talk about how shaky it is later. But 5 Earth masses is the number in the literature, and it is the number people use. The second figure is the volume. The outer boundary at 100,000 times the Earth's distance from the Sun gives a sphere containing about 10 to the 49 cubic meters. There is no controversy in that. It is just geometry. Divide one by the other, and you get the average density of the Oort cloud, smeared out over its own volume. The answer is about 2 times 10 to the minus 24 kilograms per cubic meter. That is a number with no intuitive content whatsoever, so let us give it some. The air in your room is 1.2 kilograms per cubic meter. The Oort cloud, averaged over itself, is about 1,000,000 billion times thinner than that. If you took a cubic meter of the Oort cloud, a box the size of a washing machine, drawn anywhere in that region at random, and weighed everything inside it, you would be weighing about 2/millionths of a millionth of a millionth of a millionth of a gram. It is not a small amount of material. It is a rounding error on nothing. Fine, you say. It is empty space. Of course it is empty. That is not surprising. So here is the comparison that makes it surprising. Our solar system is currently flying through a wisp of interstellar gas. It is called the local interstellar cloud. It is about 30 light-years across, and the Sun entered it somewhere between 44,000 and 150,000 years ago, and will leave it in another 10 or 20,000. It is warm, around 7,000 Kelvin, though that word means almost nothing at these densities, and it is, by any human standard, an absolutely perfect vacuum. It contains about 0.3 atoms per cubic centimeter. Not molecules. Atoms. 3 atoms in every 10 cubic centimeters of space, which is roughly 1/10 of a shot glass. The best vacuum ever produced in a laboratory on Earth, using every technique we have, is about 30,000 times denser than that. Now convert those loose atoms into a density, the same way we did for the comets. 0.3 hydrogen atoms per cubic centimeter works out to about 5 times 10 to the minus 22 kilograms per cubic meter. And the Oort cloud was 2 times 10 to the minus 24. The gas is about 236 times denser than the comets. Let me say that in plain words, because it took me a while to accept it. The great frozen shell that we draw as the outer boundary of the solar system, the trillion objects, the 5 Earth masses, the thing on every diagram, contains, per cubic meter of the space it occupies, about 1/200th of the material that is already there, in the form of thin interstellar gas. The near vacuum that the Sun happens to be drifting through, the gas we describe as essentially nothing, outweighs the entire Oort cloud by a factor of more than 200 to 1 in the same volume. The comets are not what that region is made of. The near vacuum is what that region is made of. The comets are a garnish. I want to be clear about the standing of that claim, because it is my arithmetic, rather than a sentence I am quoting out of a paper. But the two inputs are not controversial. 5 Earth masses and 0.3 atoms per cubic centimeter are both standard published values that you will find in NASA material and in review articles. And the conclusion is robust. Halve the gas density and double the comet mass, and the gas still wins by about 60 to 1. There is no plausible revision of either number that flips the result. And there is a version of this that is even harder to shake off. 1 cubic light-year of the local interstellar medium contains roughly 70 Earth masses of gas. The entire outer Oort cloud, out to 1.5 light-years, contains about 5 Earth masses of comets. So if you drew a single cubic light-year, one box, out of the many that make up the cloud, the thin gas inside that one box outweighs every comet in the whole Oort cloud by more than 10-fold. There is a useful way to see why this is not a paradox, and it is worth a moment because otherwise it just sounds like a trick. The comets carry almost all the mass out there in condensed form, packed into solid objects, ice and rock, at densities not far off water. But condensed matter takes up almost no room. 1 trillion kilometer-wide objects sounds like a great deal of stuff, and it is. But if you collected every one of them and pushed them together into a single ball, that ball would be smaller than the Earth. And you would then be left with a sphere 1.5 light-years across, containing one Earth-sized rock and nothing else at all. The mass was never the problem. The volume was. Nothing in human experience prepares you for a container that large, and the mind quietly refuses to divide by it. It is the same category of surprise as the asteroid belt, only taken much further. Every science fiction film shows a spacecraft weaving frantically through tumbling rocks, and the reality is that spacecraft cross the asteroid belt without collision avoidance maneuvers at all, because the average separation between asteroids there is something like 1 million kilometers, and the odds of hitting one by accident are negligible. That already feels wrong to most people. The Oort cloud is that same surprise, multiplied by several thousand, and then multiplied again. So think about what we have actually been doing tonight. We set out to travel to the edge of the solar system. We spent tens of thousands of years getting there. We arrived, in a manner of speaking, at a place with no boundary, containing objects we cannot see, spaced further apart than the outer planets. And now we find that the region we crossed all that space to reach is, per cubic meter, less substantial than the empty space around it. The thing we drew on the map as the outer limit of everything the sun holds is thinner than the nothing it sits inside. That is not a poetic flourish. It is a division sum. And it has a practical edge too, which is easy to miss. It means the dominant hazard on this journey is not the comets. Nobody planning a crossing of the Oort cloud would waste a moment worrying about collision with one of the trillion objects. The odds are so far beyond negligible that they do not enter the design. What the ship would actually be flying through, continuously, for tens of thousands of years, is that thin interstellar gas, a few atoms per cubic centimeter, hitting the hull at 17 kilometers a second, one atom at a time, grinding at the leading surfaces. The named feature of the region turns out to be irrelevant to the trip. The unnamed background is the thing that would eventually wear the ship away. And I think it explains something about why this region resists being pictured. Every image of the Oort cloud shows a dense spherical haze, thick with objects, a shell you could see. That picture is not merely an exaggeration. It is inverted. The truth is that if you could somehow perceive the mass around you out there, the comets would not be the pattern. The gas would be, and the comets would be a scattering of impossibly rare specks inside it, one every few billion kilometers, contributing almost nothing. But they are there. A trillion of them. Real objects with real surfaces, sitting in the dark. So let us finally go and look at one. Because I have spent most of this video telling you what you would not find out there, and I promised you what you would. Let me hand you a lamp and put you on the surface of one. You have found it by a fluke of trajectory that would not repeat in a million years, and you have matched speed with it, and you have come down. The gravity is so slight that landing is not really the word. You approach, you touch, and you stay, because nothing has told you to leave. If you jumped gently, you would not come back. You switch the lamp on and point it at the ground, and almost nothing comes back. The surface is black. Not dark grey, not dusty, black, in the way that printer toner is black, absorbing something like 95% of everything you throw at it. Your beam goes into it and stops. The pool of light at your feet is dim and small, and has no shine anywhere in it. The horizon is close, because the object is a few kilometers across, and it is not a smooth horizon. It is jagged and lumpy and irregular, because nothing out here has enough gravity to pull itself into a ball. Beyond that edge there are stars, all the way down, past where the ground ought to continue, because you are standing on something small enough that the sky is underneath you as well as above. It is 2.7 Kelvin, colder than liquid helium, colder than anything on Earth outside of a specialized laboratory. And the reason it is not colder is the microwave hiss of the early universe, arriving from every direction, doing what our star can no longer do. Under your boots, a meter or two down, is water ice that has not been warmed since before the Earth had a surface. Trapped inside that ice, in tiny pockets, is carbon monoxide that has been waiting 4.5 billion years for a reason to leave. Nothing has ever happened here. There has been no impact, no heating, no weather, no light worth speaking of, no motion except a slow rotation and an orbit so wide it has been completed perhaps 140 times since the object formed. If you scuffed the surface with your boot, that scuff would be the first event in the object's history since it arrived. Now let me tell you how we know all of that, because we have never been anywhere near one of these things. We know it from comets. Every physical fact anybody has about the contents of the Oort cloud comes from studying long-period comets on their way in. Objects that were out there, got nudged, fell inward for a few million years, and arrived close enough to the sun to start coming apart while we watched. And what those comets tell us is chemically specific. Surveys of the volatile content of Oort cloud comets find high abundances of carbon dioxide, carbon monoxide, and methanol relative to water. Those are what astronomers call supervolatiles, substances so easily driven off that they cannot survive as ices anywhere warmer than the outer solar system. The presence of nitrogen and molecular oxygen has also been detected. These are materials that exist in solid form, essentially nowhere else in the solar system's inventory, except in the deep cold. And there is a beautiful piece of physics in how they are stored. The carbon monoxide and carbon dioxide are not sitting in neat separate layers of their own ice. They are trapped inside the water ice, and specifically inside amorphous water ice, which is water frozen so cold and so fast that its molecules never got the chance to arrange themselves into a crystal. Amorphous ice is a disordered solid, full of gaps, and gas molecules get caught in those gaps as it forms and cannot get out. Which sets up something remarkable. When one of these objects finally falls inward and begins to warm, even slightly, long before it is anywhere near warm enough to melt or evaporate water, the amorphous ice starts to reorganize itself into proper crystal. And as it does, it closes up the gaps and expels the trapped gas, all at once, from beneath the surface. That is why comets can be violently active at distances where sunlight is far too feeble to do anything to water ice. It is not the sun boiling them. It is the ice rearranging itself and letting go of something it has been holding since before the planets. Comet C2017 K2, Pan-STARRS, was found to be active well beyond the distance where crystallization begins, and it is one of the clearest examples of the effect anybody has. Now, the surfaces. The word people always reach for with comets is pristine, and comets genuinely are the most compositionally pristine objects in the solar system, material that has sat, unaltered, since the disk that made the planets was still forming. But pristine is not the same as untouched, and the outside of these objects is not the inside. For 4.5 billion years, out there in the dark at 5 or 6 Kelvin, they have been sitting in a continuous rain of galactic cosmic rays, high-energy particles from elsewhere in the galaxy, arriving from all directions with nothing to stop them. Inside the solar system, the sun's magnetic bubble screens out something like 70% of that flux. In the Oort cloud, there is no such protection. Modeling of what that exposure does is unambiguous. The radiation converts crystalline ice into amorphous ice. It compacts porous material, and, over long enough, it breaks apart the water-dominated matrix and drives the chemistry toward long-chain hydrocarbons, complex, heavy, carbon-rich organic molecules that are dark. Over billions of years, this builds an irradiation crust, a processed rind, perhaps a meter or more thick, sitting over material that is genuinely primordial underneath. So the object under your boots is two things at once. It is the best preserved sample of the early solar system that exists anywhere. And it is wearing 4.5 billion years of radiation damage over the top of it, which is the only part you can see. Let me give you the real objects now, with names and dates, because after all this abstraction you deserve some. The first is Comet C 2014 UN 271, which everyone calls Bernardinelli-Bernstein, after the two astronomers who found it. It was recovered in 2021 from archival images taken by the Dark Energy Survey. Pedro Bernardinelli and Gary Bernstein went back through years of data and found it sitting there, first recorded in October of 2014, at about 29 times the Earth's distance from the Sun. When Hubble measured its nucleus in 2022, the answer came back at roughly 137 kilometers across. That is the largest Oort cloud comet ever found, by a very wide margin, 10 times the diameter of a typical comet nucleus, an object the size of a small country, a mountain range with an orbit. In 2025, the ALMA array in Chile detected molecular activity coming off it at 16.6 times the Earth's distance from the Sun, the first time molecular activity has been seen in an object that large at that range, and at that distance it cannot be water doing it. It has to be a supervolatile. It is the crystallization mechanism, caught in the act. Its far point is somewhere between 40,000 and 59,000 times the Earth's distance from the Sun, depending on which part of the orbit you fit. Which means it is a genuine outer Oort cloud object. It has spent millions of years out there in the cold, and it is arriving now, in our lifetimes, and it will reach its closest approach to the Sun on the 22nd of January, 2031. At 10.9 times the Earth's distance, which is just outside Saturn's orbit. It will never come close. It will never be visible to the naked eye. There will be no great comet in the sky. But it is, as near as anybody can manage, a piece of the Oort cloud delivered to us. And it is the closest thing to a photograph of that region that this generation is going to get. The second object is Sedna, and Sedna is different because Sedna may still be out there rather than falling in. It was discovered on the 14th of November, 2003, by Michael Brown, Chad Trujillo, and David Rabinowitz at Palomar. It is about 1,000 kilometers across, roughly the width of France, and it is one of the reddest objects in the solar system, a deep rusty color attributed to tholins, the complex organic residues that form when methane and nitrogen ices are irradiated for long enough. Which is to say, Sedna is wearing the same crust we were just talking about, and we can see its color. Its orbit is the thing. Its closest approach to the Sun is about 76 times the Earth's distance, well beyond Neptune, well beyond the Kuiper Belt. Its farthest point is about 937 times the Earth's distance. One orbit takes about 11,400 years, and it spends the overwhelming majority of that time out beyond 500 times the Earth's distance, where it simply cannot be seen at all. And here is why it matters. Sedna's closest approach is too far out for Neptune to have put it on that orbit. Neptune cannot reach it. Something else did, a passing star, or the galactic tide, or something in the Sun's birth environment. Sedna is detached, and its discovery provided the first observational evidence for a population in the inner Oort cloud. Two more have joined it since. An object called 2012 VP113, found a decade later on a similar orbit, and one called Leleakuhonua, further out still. Which brings us back to where this video started, and to the sentence I promised you would hear again. The Oort cloud was discovered by counting the wreckage. And every single object I have just named you, Bernardinelli Bernstein, Sedna, Halley, Hale-Bopp, is wreckage. Every one of them is something that got knocked out of the region and fell close enough to be caught. 76 years of better telescopes have not changed the method one bit. We have simply got better at watching the pieces come down. Not one object has ever been confirmed sitting in place, out there, where it lives. And there is a quiet bias built into that which is worth naming, because it colors everything we think we know. The comets we study are, by definition, the ones that survived the trip-in and held together long enough to be observed. Many do not. They crumble, they fragment, they evaporate, they hit something. So the sample is a survivor sample. Every physical measurement in the field is taken on the subset of objects tough enough to arrive, which may be nothing like the average. There is a second layer to it too. The only comet any spacecraft has ever spent real time alongside is 67P, which Rosetta orbited for 2 years, and 67P is not an Oort cloud object at all. It is a short-period comet from the scattered disk, a different reservoir entirely, formed and stored under different conditions. Our single best, most detailed dataset on cometary material comes from the wrong place. Everything we say about the contents of the Oort cloud rests on remote observation of objects at a distance, and always has. So something is knocking them loose. Something reaches into that region on some rhythm and pushes. And it is not the Sun. There is a tide going out somewhere on Earth right now, and the reason is that the Moon does not pull on the whole planet equally. The side facing the Moon is a little closer, so it gets pulled a little harder. The far side is a little further away, so it gets pulled a little less. The difference between those two pulls stretches the Earth very slightly along the line to the Moon, and the oceans, being liquid, respond by bulging. That difference, that stretch, is what a tide is. It is not a force in its own right. It is the leftover, the inequality in somebody else's gravity across the width of the thing being pulled. Now do that to the solar system, with the Milky Way doing the pulling. The galaxy has 100 billion stars or more, and a great deal of unseen mass besides, and all of it is arranged in a disk that our Sun sits inside, about 26,000 light-years from the center. The galaxy's gravity acts on the Sun and on everything the Sun holds. Close in, that does not matter at all. The Sun's own grip on Mercury is so overwhelming that the galaxy is an irrelevance. But the Sun's grip weakens with distance, and the galaxy's does not weaken appreciably across the width of a solar system. And so, as you go outward, there comes a point where the difference in the galaxy's pull from one side of an orbit to the other starts to be comparable to the Sun's own hold. That is the galactic tide, and out in the Oort cloud it is a major player. The detail that makes it interesting is that it is not symmetric. The pull toward the center of the galaxy exists, but the dominant component, the one that actually does the work, is the pull perpendicular to the galactic disk, the vertical squeeze from all the mass in the plane above and below us. At the Sun's distance from the galactic center, that vertical tide has been estimated to be about 10 times more effective than the radial one at perturbing Oort cloud comets. And it is especially efficient in a particular band, at semi-major axes of roughly 30 to 40,000 times the Earth's distance from the Sun, where it drives slow, regular oscillations in how close a comet's orbit brings it to the Sun. Which gives us, finally, the mechanism. This is how comets happen. An object out there is on some long, slow orbit, and the galactic tide, working on it for millions of years, gradually swings the closest point of that orbit inward. Not quickly, a little each lap. And eventually, after a long time, that closest point drops far enough that instead of turning around at 2,000 times the Earth's distance from the Sun, the object turns around at 3 or 4, inside the planets, inside the light, inside the zone where its ice can finally do something. It warms. It sheds. It grows a tail. Somebody on Earth photographs it and gives it a name. Astronomers have a phrase for the narrow band of orbits that qualify, the loss cone. Fall into the loss cone and you become a comet. But the tide alone cannot explain the numbers. It empties the loss cone faster than it can refill it, which would mean far fewer comets than we actually see. So there has to be something else, and the something else is passing stars, which stir objects into the cone from the outside, from regions the tide cannot reach. The current understanding is that the two mechanisms work together in a way that produces more comets than either would produce on its own. Which of them dominates depends on how far out the cloud really extends. For a big, extended cloud, the tide wins. For a compact one, the passing stars do. And we cannot yet tell which of those we live in. So let us look at the stars, because the numbers there are the ones that finish the argument. Using measurements from the Gaia spacecraft, which has mapped the positions and motions of well over 1 billion stars, astronomers have worked out how often other stars come close to us. The answer is that somewhere between 19 and 24 stars pass within 1 parsec of the Sun in a typical million years. 1 parsec is 3.26 light-years, roughly twice the outer radius of the Oort cloud. Broader counts put around 550 stars within about 150 trillion kilometers per million years. 20 stars per million years sounds sparse. It is not, and here is why. An object at the outer edge of the Oort cloud takes 31.6 million years to complete one orbit around the Sun. Multiply it out. During a single lap, one orbit, one circuit, the smallest complete unit of that object's existence, roughly 600 stars pass within a parsec of our Sun. 600. Some of them much closer than that. The outer Oort cloud is not a stable orbital system in the way the planetary region is. The planets have been going round in essentially the same orbits for 4.5 billion years, and they will keep doing it. The outer cloud is a population that gets reshuffled hundreds of times before any individual member finishes one lap. Orbits out there are not permanent arrangements. They are temporary conditions between disturbances. And remember what it takes to disturb them. Escape velocity out at the edge is about 133 meters per second. A passing star does not need to do anything dramatic to strip an object away entirely, or to swing it inward, or to change its orbit beyond recognition. It needs to change the object's speed by rather less than the muzzle velocity of a rifle. That is all. That is the margin the Sun is holding by. There is a third perturber worth a sentence, and it is the rarest and the most violent. Giant molecular clouds, the enormous cold complexes of gas and dust where stars are born, hundreds of thousands of times the mass of the Sun, drift through the galaxy too, and if the solar system passes near one, the tidal effect is not a nudge. It can strip a substantial fraction of the outer cloud away in a single encounter. That happens perhaps once every few 100 million years, which means it has happened to us a good number of times already. The Oort cloud we have today may be what is left after several such robberies. And this whole machinery is not even running at a constant rate. The Sun does not sit still in the galactic disk. It bobs slowly up and down through the plane, taking tens of millions of years to complete each oscillation. As it rises above the midplane and sinks back, the strength of that vertical tide changes with it. So the rate at which comets are being sent inward has been rising and falling on a rhythm of tens of millions of years for the whole history of the solar system, driven by the Sun's own position in the galaxy, which means the comet supply is set by something happening thousands of light-years away. Two encounters are worth naming, briefly, because they show that this is not theoretical. A small red dwarf called Schultz's star is calculated to have come within about 0.8 light-years of us around 70,000 years ago, with a 98% probability that it passed straight through the outer Oort cloud while our ancestors were alive to see it go by, entirely unaware. And a star called Gliese 710, currently about 60 light-years away, is calculated to pass within about 0.17 light-years in roughly 1.3 million years, deep inside the cloud, not skimming it. It also means the traffic runs both ways. If a passing star can push an object inward to become a comet, it can just as easily push one outward, past escape and out of the solar system entirely. That has been studied directly. A paper in Astronomy and Astrophysics in 2019 looked at the galactic tide and local stellar perturbations, specifically as a mechanism for creating interstellar comets, objects that leave one star's cloud and wander the galaxy unattached. Which means the Sun is not only being robbed, it has been shedding its outer cloud, slowly, for 4.5 billion years, and some of what it has lost is out there now, drifting between the stars, or already caught by somebody else. So who is in charge out there? Not the Sun, or at least, not the Sun alone. It supplies gravity, but a hold so weak that a rifle shot's worth of velocity breaks it, against a galaxy that squeezes the region continuously, and hundreds of stars that walk through it each lap. It supplies light, but by the outer edge, it is serious. It supplies heat, but past 10,400 times the Earth's distance, the cosmic microwave background supplies more. Every criterion by which we normally say that something belongs to a star is weak out there. Gravity, barely. Light, no. Heat, no. There is one criterion left, and it is the one everybody assumes is unarguable. Common origin. Whatever else may be true, those objects formed here, in our disk, around our Sun, they are ours because they were made here. That is the part that turns out not to be true. Before the answer, let us clear the ground, because there are two things people expect to be out there, and neither of them is. The first is a companion star. In 1984, two independent groups proposed that our Sun has a faint partner on a very long, very stretched orbit, a dim red dwarf or a brown dwarf that swings through the Oort cloud every 26 million years or so, shaking comets loose and sending them inward in showers. It was given the name Nemesis, and the reason for proposing it was that somebody thought they saw a periodicity in the fossil record of mass extinctions with roughly that spacing. This was serious science. It was published in Nature. It was a real hypothesis, testable, and taken seriously for years. And then it was tested. The Wide Field Infrared Survey Explorer surveyed the entire sky in infrared, which is precisely the wavelength at which a cool, dim companion would be conspicuous, and it found nothing. No companion. Meanwhile, the claimed periodicity in the extinction record weakened badly under reanalysis. Nemesis is gone, not suppressed, not covered up, simply proposed, examined, and ruled out. That is the system working exactly as it should, and the people who proposed it were not fools. They were doing the job. The second is the family of claims that something large is out there and known about and being hidden, the Planet X and Nibiru material, which often uses the Oort cloud's fuzzy boundary as evidence that somebody is being evasive. The answer does not require you to trust anybody. A body massive enough to matter would tug measurably on the orbits of the outer planets and the known objects beyond Neptune, and those orbits are tracked continuously by many independent groups in many countries with no ability to coordinate a story. An object actually inbound would show up in infrared all-sky surveys long before arrival, and those surveys have been done and are public. And the vagueness of the outer boundary is not a hedge. It is the honest consequence of a region defined by where a star's gravity fades rather than by any surface. NASA writes on its own public pages that the outer boundary is not sharply defined. Concealment does not usually look like publishing the uncertainty. There may well be something substantial out there, incidentally. The Planet 9 hypothesis proposes a body of several Earth masses at several hundred times the Earth's distance, on the basis of clustering in the orbits of objects like Sedna. It has not been found. It may not exist. But if it does, it lives in that badly mapped region between the Kuiper Belt and the inner Oort cloud, and its existence would only confirm what this whole video has been saying, which is that our knowledge of the solar system falls apart quickly, past a few hundred times the Earth's distance from the Sun. So, the terrifying journey to the Oort cloud, and what you would really find. The first answer is the honest one, and it is nothing. Not nothing as a disappointment. Nothing as the actual finding. You would cross tens of thousands of years and hundreds of billions of kilometers and arrive at a region with no boundary, containing no detectable objects, at 2.7 Kelvin, in a dark that defeats every instrument, with your star reduced to a point about as bright as Sirius, in a volume per cubic meter less substantial than the interstellar gas outside it. The emptiness is not a failure to find things. The emptiness is the discovery. The outer boundary of everything our Sun holds is not a wall or a shell or a swarm. It is the thinnest place we know how to point at. The second answer is about the things that are there, and it is a correction to the picture rather than an absence. They are not white. They are black, tarred by 4.5 billion years of cosmic rays into a crust of long-chain carbon compounds a meter or more thick, reflecting about as much light as printer toner. They are colder than liquid helium, and they are kept at that temperature not by our star, but by the microwave afterglow of the beginning of the universe, which took over from the Sun somewhere around 10,450 times the Earth's distance out. They are drifting around the Sun slower than a bullet train, on laps that take 31 million years. And underneath that black crust, meters down, they hold the most pristine material anywhere in the solar system. Water ice never warmed since before the Earth had a surface, with carbon monoxide trapped inside it, waiting. They are, in other words, exactly what you would want to find, wearing a disguise that makes them impossible to see. And then there is the third answer, which is the one I have been holding back all night. The models do not work. Take the standard story of how the Oort cloud formed, objects assembled among the giant planets, in the region between Jupiter and Neptune, then flung outward by gravitational encounters with those planets over millions of years, until they ended up on enormous distant orbits. That process is real, and it does produce a cloud. But when you model it carefully, and compare the result with what the comet statistics actually demand, it comes up short. The Oort cloud we observe is substantially more populous than the models can account for. There are too many objects out there. Our own giant planets could not have put that many there. In 2010, in the journal Science, Harold Levison, Martin Duncan, Ramon Brasser, and David Kaufman published a resolution. The Sun did not form alone. Almost no star does. Stars form in clusters, hundreds or thousands of them together, packed close in the same collapsing cloud of gas, and while that cluster holds together, the outer reaches of all those young systems overlap. Each star is flinging debris outward. Each star is surrounded by loosely held material, moving at speeds of a few hundred meters per second. And under those conditions, material thrown out by one star can be captured by a neighbor, and material thrown out by the neighbor can be captured by you. Their simulations show that process working, and working efficiently. And the conclusion in the paper is this: a substantial fraction of the comets in the Sun's Oort cloud, perhaps exceeding 90%, came from the protoplanetary disks of other stars. 90%. The paper names names: Halley, Hale-Bopp, McNaught. Comets that people have stood in fields and watched and remembered for the rest of their lives may have been assembled in orbit around a star that is not ours, and taken and kept. I want to be careful here, because this is a modeling result and not a measurement. It resolves a real quantitative discrepancy. It was published in a major journal, it has been widely cited, and work has continued on Oort cloud formation in star clusters since. But the 90% is a simulation output with genuine uncertainty attached, not something anybody has confirmed by going and looking, and nobody is going to go and look. What is solid is the shortfall. There are more objects out there than our own planets could have made, and capture from sibling stars is the leading explanation for the excess. So take the whole journey and stand at the end of it. You cannot point at it, not from the Earth, and not from inside it, because there is not one object out there whose position anybody can indicate. It was discovered by counting the wreckage, and 76 years later, that is still the only method, and every object we can name is a piece that fell out. And out here the Sun is just a star, one point among many, holding on by a rifle shot's worth of velocity, out-heated by the Big Bang and out-muscled by the galaxy. And most of what is out here came from a different one. That is what you would really find at the edge of the solar system. Not our outermost layer. Not our final shell. A communal inheritance from a nursery that dissolved 4.5 billion years ago, assembled from dozens of stellar systems that have long since scattered across the galaxy and will never be identified. The last physical evidence that our Sun ever had a family, held at arm's length in the dark, at the temperature of the early universe, for longer than the Earth has had oceans. The Sun's siblings are out there somewhere tonight, unrecognizable, scattered around the Milky Way. And each of them, if the models are right, is carrying some of ours. We have never seen any of it. 76 years after Jan Oort sat down with 19 comets in a cold January in Leiden, that has not changed, and there is no plan anywhere that would change it. The largest structure attached to our star remains, in the words of one review of the field, an unobserved intellectual concept. It is out there, in every direction from where you are lying, right now. And it will still be there in the morning, doing nothing at all, very slowly, at 2.7 degrees above absolute zero.